All right, everybody, welcome. Happy, well, Sunday now, but hopefully you're reading this, seeing this on a Monday. Happy Monday, everyone. Hope you're doing well out there in quarantine land. I know it's been a rough go, but I'm proud of you all. Keep going. What I want to do today is I'm recording this video so I can explain to you a little bit about your proof project and the kind of proofs that I want you to do for your project. I have it up here. You see the proof project. I want to go through it a little bit and then explain a little bit about induction, contradiction, and what a direct proof is, and talk about what I'm expecting. So in the project, I wanted you to use one of these kinds of mathematical proofs or an explanation of a mathematical proof to demonstrate a mathematical, theorem that it's true. Math is built on evidence, and math is built on proofs. To show that something is true, to show that something works, we need to have a proof. That's how, otherwise, how can we be sure? Math wants to be sure, and one way to be sure is by proving what your theorem is. So there's three kinds of proofs I have here: induction, contradiction, and direct proof. I'm going to talk a little bit about those today. Your project, I'm reading here, your project will be to use one of these methods to prove one of the mathematical equations we've used in class, I'm going to use here, or to find and explain another mathematical theorem that has been proven. So this is a two-part kind of project. You can either do a proof that I'm going to show you some examples of, and you can use those examples to do one of the proofs that are listed below. Or you can do a research project about a proof and do an explanation using someone else's ideas and explaining what it was that they proved, what the theorem is. I had a lot of good examples last year of people doing things like proving different sizes of infinity, or proving the quadratic formula, or proving just lots of very interesting things. So I'm going to post some of those examples so you can see what kind of things I'm looking for. But to have a mathematical idea accepted, again, by others, you have to formally present your findings in a symposium or other educational gathering and defend your idea. So this is the goal, right? You do your proof, and then you demonstrate it to everybody else. There's three parts to this project that I'm going to want you to turn in. You're going to have a proof, so the math behind what you're doing. I want you to have an explanation. That's some writing explaining what it was that your proof shows and what it does. And then a demonstration, and this was going to be the thing we do in class. But depending on how things are going, I may have a video or may adjust that part of the project. We'll see. But I'm going to show you today what the kind of proofs I'm looking for are like, how you do them, and so you can use those as pieces in your project. Okay. So let's get into proof by induction. I'm going to show you what induction is first, and hopefully this will help you. So induction, let's go induction. Got a neat thing here. Induction. What is induction? Mathematical induction is kind of like, you can think of it like dominoes. So mathematical induction is you have evidence of something that is true for the first case, for the first situation. You know it's true in one case. You assume that it's true for most of the cases, and then you show that it's true for the next case. And if it's true for the first situation, and it's true for the next situation, then that knocks all the dominoes down, and you know that it's true for every possible situation, for every possible number. So if it's true for one number, and it's true for the next number, that first one knocks into the next one, which knocks into the next one, next one, all the way down, proving that it's true for every single number. Like, there's a lot of interesting ideas out there that work for most of the numbers, or some numbers. But you don't want to spend your time going through, well, it works for this number if I plug in a 1, does it work if I plug in a 2? What about if I plug in a 3? What if I plug in a 4? What if I plug in a 5? You spend forever doing that. And the idea behind induction is that it makes it so you don't have to plug in every number. You show that it works for every number by using this domino effect. You show it works for one, and then you show it works for the next situation, and that proves that it works for all the situations. So induction has has basically 3 steps, right? 3 steps. The first step is you show that it works, show that it's true, show it's true for some situation n equals 1. Hold on, let me fix that. Some situation where it is n equals 1. You show it's true for the first situation. The next step is you assume that it's true for some n equals an arbitrary some amount of numbers. It's true for 1, so it's got to be true for some amount of numbers. And then the third step is you show that it's true for the next n, k plus 1. You show that it's true for the next step, right? So if you show that it's true for the first situation, you show that it's true for the next situation, k plus 1, that means it's going to be true for every situation. If it's true for the first one and the next one, well, that first one knocks the next one. If it's true for the first one, that means it's true for the second one. If it's true for the second, that means it's true for the third one, and the fourth, continuing down. So that plus 1 step, that's the critical step. So how do we use this? Let me show you an example. One thing we're going to prove is we want to prove that the sum of n odd numbers is equal to n squared. But if I add up some number of odd numbers, I get that number of odd numbers squared. Let me show you an example. So if I have the number 1, that's equal to 1 squared. That's fine, right? Here's my example. If I have 1 plus 3, the first odd number plus the next odd number, and that's 4, which is 2 squared. If I do it again, let's get the next odd number. 1 plus 3 plus 5. 1 plus 3 is 4, plus 5 is 9, which is 3 squared. So what we're doing is I'm showing you here is n equals 1. Here's n equals 2. I have 2 odd numbers, and it equaled to 2 squared. And here is n equals 3 odd numbers, 1, 2, 3, and it was 3 squared. So it seems like this is true. If I keep going, I can do the next one. What's the next one? If I go 1 plus 3 plus 5 plus 7. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, which is 4 squared. 1, 2, 3, 4 odd numbers makes 4 squared. And so it would seem that if I add up some number of odd numbers, I'm going to get n squared. But let me show you how we do this in a proof. Let's do a proof of this. So our proof, again, our induction has 3 steps. Step 1, show that it's true for n equals 1. Well, we did that for 1 is 1 squared, so that is good to go. 1 is equal to 1 squared. Step 2, we assume that it works for some n equals k. So I'm going to say 1 plus 3 plus dot 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 plus the kth or nth, whatever, odd number, the next odd number, the last odd number. Now I need to have an odd number here. I need this to be odd numbers, right? And I know that an odd number is equal to 2n minus 1. That's my odd number. Remember we talked about patterns, right? 2n minus 1, this is an odd number. Right? Even numbers is anything that is 2 times some number. Even numbers divisible by 2. Odd number, take the even number and minus 1. So it's 1 less, right? So our first odd number, if I plug in a 1 to n, 2 times 1 is 2 minus 1 is 1. First odd number, right? Second odd number, So odd numbers are 2n minus 1. Even numbers are 2n. So my next odd number here is going to be 2 2k minus 1. And I'm going to assume, let me not use k, let me use n, just because it's easier. 2n minus 1, and that's equal to n squared. That's what I'm assuming that, okay? 2n plus 1 is equal to, 1 plus 3 plus 2n minus 1 is n squared, right? I add n odd numbers, and it's equal to n squared, right? Because odd numbers are 2n minus 1, odd numbers. I got to put 2n minus 1. That's my nth odd number right there. So that's, I'm assuming, is true. My next step is show that it works for k plus 1. So if I do 1 plus 3 plus dot 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 plus 2n minus 1, right, there's my nth odd number. And now I add on the next odd number, which is going to be 2 times k plus 1 minus 1. Right? So this is my nth number right here, the nth odd number, or kth odd number. We should go back to k. Going back to k here. Maybe do k here too. So this is going to be 2k minus 1. And this is going to be 2k minus 1. So I have 2k minus 1. This is my kth number. It should be k squared. K squared. And so I have all those numbers equal to k squared. That's my kth odd number. Now if I have k plus 1, I have all those previous ones plus the next odd number, k plus 1 minus 1. So there's a couple tricks, right? And that should equal k plus 1 squared, right? So add it up, k odd numbers, some amount of odd numbers, right? Here's step 2. I added up some amount of all the odd numbers equals that amount squared. Now I'm going to show that if I add up all those plus the next one, 2 times k plus 1 minus 1, right? Here's my 2k minus 1, 2k plus 1 minus 1. It is k plus 1 squared, the next step. And there's a couple important pieces of this. Here, all of this is all of this. We used that before. And that is just k squared, right? So we're going to use step 2 in step 3. And this is going to be true for all the proofs you do, using this assumption in the third step in the next step. And then we're going to say this k squared plus this next thing. So I'm going to distribute the 2 here. Get 2k plus 2 minus 1 should be equal to k plus 1 squared. So this is what I want to prove. I want to prove that all these things added together equal the same thing. So if I rearrange this a little bit, let me do the part in red. So if I go k squared plus 2k, 2 minus 1 is plus 1, that should equal to this thing here, k plus 1 squared. K plus 1 squared, when the parentheses are squared, remember, don't kill puppies, that means k plus 1 times k plus 1. So if I do distribution here, I should get k squared plus 2k plus 1, and look at that, these two sides are the same. A squared plus 2k plus 1. And that's my proof. QED. Now, QED is just a little fun thing that means quod erat demonstratus. It's a little Latin, and it means, and so it is proved. So that's a proof by induction. You assume the first step. You say 1 equals 1 squared. You show it works for the very first step. You assume it works for all these up to this k number, 2k minus 1. Remember, we're doing odd numbers, so that was my 2k minus 1. And I assume that equals k squared. And then I show that it works for all those numbers plus this next number, 2k plus 1 minus 1, my next odd number. This is my next odd number, right? This is the 2k plus 1 step, right? 2k plus 1 minus 1. That's the next odd number, and it equals to k plus 1 squared, right? And we did a little bit of algebra, simplified some stuff, we show they're the same. And that's a proof by induction, right? So those 3 steps, if you follow those 3 steps, you'll be able to do this. Let me show you another one. There's another example. So what I want to do is prove that I want to prove that 1 plus 2 plus 3, if I add up all the integers, dot, 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 plus n numbers, that it's equal to n times n plus 1 over 2. If I add up some amount of numbers, call this 4, plus dot, 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 1 plus 2 plus 3 plus 4, all the way up to n, add them up, you get this equation over here, n times n plus 1 over 2. This is what I want to prove. I want to show that if I add up all those, it equals that equation. So let's do induction. The first step, show it's true. Oh God. Show it's true for n equals 1. So for 1, I want to show that the 1 by itself, if I plug 1 into my formula, it equals 1. So that's going to be 1 times 1 plus 1 over 2. So 1 times 1 plus 1 is 2 over 2. That's 2 over 2, which is 1. And so, yes, my equation is good. I know it works for the first situation. I plugged in a 1. Plugged in a 1, plugged a 1 in my formula, I showed that it works for 1. I could show it works for some other ones. If I did 1 plus 2, and that's 3, right? I want to show that's equal to, I have 2 numbers. Here was 1, 2, right? Here was 1 number. That's why this was a 1 plus 1 over 1. For 2 numbers, I would have 2 times 2 plus 1 over 2. And that would be right. So the 2 is because it has 2 numbers. 2, right, plus 2 plus 1. Here it was 1 plus 1, so 1 number. So 2 plus 2, that's going to be 2 times 3 over 2, which is 6 over 2, which is 3. And that also works. So we're good. So we can keep going, but I know it works for the first situation. Let's do the induction step. Step 2 is assume that 1 plus dot 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 plus n is n times n plus 1 over 2. I'm assuming that it's true. So I'm going to show my induction step, show 1 plus 2 plus dot 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 plus n plus n plus 1. My next step is, and I'm going to plug in here, I'm going to plug in the n plus 1s. So this is going to be n plus 1 times n plus 1 plus 1 over 2, right? So here was my next piece, n plus 1, right? I plug that into the equation as n plus 1, and I need to show that all those things added together plus the next piece equals this new formula. And like before, all the previous stuff is this. N times n plus 1 over 2. All that is the thing I already know. So I'm adding to that this n plus 1, and it should equal this new formula over here. So, how do I do this? Let's see. Let me see if I can give myself a little bit more room here. There we go. Okay. So erase this line. So what I want to do is rearrange this side of the equation, simplify this to make it equal the same thing over here. So I'm going to do a little bit of simplifying. This is, I'm going to multiply this together. Multiply these together. I'm going to get n squared plus n over 2. Now how do I know to do this? I'm just going to do some algebra. The only thing I know how to do, the only tool I have right now is just doing some algebraic manipulation. You set up your equation, and you do a little bit of algebra, and you make the two sides equal to each other. Plus n plus 1 equals this over here. This is going to be n plus 2. And then I'm going to do a little bit of, well, I'm going to leave those alone. This is going to be n plus 1 times n plus 2 over 2. I want to show that this plus this is equal to this thing over here. What can I do? What can I do? Well, it looks like I want to add these two things here, and this one's not a fraction. Right now it's over 1. So if I multiply this side here by 2 on the top and a 2 on the bottom, then I can add these two things together. So n squared plus n over 2 plus multiply these by 2, 2n plus 2 over 2. And then if I combine these into one big fraction, it'd be n squared plus n is 3n plus 2. And I want to show that that is the same as n plus 1 as this over here. So we're close. If I did some distribution to this side, if I multiply these together, I would get n squared plus 2n plus n plus 2 over 2. If I simplify that, I'm going to get n squared plus 3n plus 2 over 2. And look at that. These two things are the same. Right over there. Over there. Over there. Can't tell which side I'm on. But that's our proof. Done. Q, E, D. So we showed that the one side, if we have the induction step, we take all the pieces plus n plus 1, the next step, it's equal to the formula we had, but in the formula I plug in n plus 1s. Plug in n plus 1. And then I do a bunch of algebra, rearranging some equations, doing some factoring, multiplying stuff together, and I get two equations that are the same, and that's your proof. Okay? That is a proof by induction. This is in section 8.4 in the book. If you're curious to read about it, section 8.4 in the book. Look through that. It'll give you a lot of demonstrations about induction. That is one of the options you have for doing your proof project. You can do this induction. There's a lot of other examples in the book that I show you, and other examples in the handout that are induction proofs. You can do a lot of different proofs by induction. Do some research online, look for an induction proof. Your job is to write it out, explain the proof, and then demonstrate the proof either in class or maybe by a video. We'll see. But I want you to do one of these proofs, and induction is one of your options. I want to go over the other options right now also with you. One of them is a proof by contradiction, and one of them is a direct proof. So there's three kind of ways that things are proven in math, or three of the ways things are proven is induction, we just did, showing your n+1 step. The next way I want to show you is proof by direct proof. What is a direct proof? Let me show you a direct proof is the next thing. A direct proof. And a direct proof is very rare in math, direct proof. Direct proofs are things where you show that something is true directly. A direct proof is like, for example, the quadratic formula. Right? Show that if you have an equation ax squared plus bx plus c equals 0, you show that with your proof that x equals, what's our song? X is equal to negative b plus or minus square root b squared minus 4ac all over 2a. Very good, everybody. Very good. Sing the song. This is a direct proof. And the way that you do this proof is by, what was it called? You're going to use completing the square. But you're just doing algebra. You're just doing algebra. You're doing this proof by completing the square. And it's just an algebraic proof, a direct proof showing that this gets you this equation here. Very rare. If you can prove that there's a formula for ax cubed plus bx squared plus cx plus d equals 0, if you're able to show that this is x equals something, some equation, right? There's about $10 million that you could earn. Something like $10 million. Someone would pay for doing this proof. It's not been shown yet. Totally open to anybody. Could be you. But people have spent a while on it and not shown it yet. So up to you. There's a lot of things like this in math. There's a lot of proofs. You can look at them. They're called the X Prize, or the Millennial Prize. Millennial Prize. If you want to look up those proofs, see if you can solve one of those. Millennial Prize in math. Could be worth your while. Could be worth your while. So a direct proof is just something like the quadratic formula. Again, you could do some research about some other direct proofs, and if you want to demonstrate one of those, that's fine. But there aren't very many, and they're not very interesting. More interesting is the next proof I want to show you, which is a proof by contradiction. Proof by contradiction. This is much more interesting and much more like common by contradiction. So I want you to use one of these kinds of proofs, or use them in your explanation. Contradiction. What is a proof by contradiction? In a proof by contradiction, you are you're stating a theorem, you're stating an idea, and you show that your idea has to be true by saying, well, what if my idea wasn't true? What if my idea was the opposite? You state a theorem, state your idea, you assume the opposite. Assume the opposite. You say, well, here's my idea, but what if my idea was wrong? And you go and do a proof that your idea is wrong. You try to prove your idea wrong. And what ends up happening is you get somewhere in your proof something that can't be true. contradiction. And when you get that contradiction, you know your original idea had to be true. Because if you did the opposite and you said, well, here, I'm going to try to prove myself wrong, and when you try to prove yourself wrong, it doesn't work. It's a contradiction. You end up with something that's impossible, and because the impossible thing can't be true, your idea had to be true. That's the idea of a proof by contradiction. You assume something, you show that you try to prove the opposite of it, you show that proving the opposite doesn't work, comes up with something that is wrong, and because the opposite is wrong, your idea had to be right. So let me show you an example of a proof by contradiction. There's a lot of these, and we know some things in math are true, but why do we know they're true? Like for example, if we add two even numbers, the sum of two even numbers is even. There's the theorem, right? We know that if we add two even numbers together, we're going to get an even number. Like, for example, 2 plus 8, and that's 10. Great. Works out. Check. 12 plus, let's call it 32. What is that going to be? 44. Well, that works out. Even number also. But is it always true? Can we prove that it's true? Can we prove that the sum of two even numbers is going to be even? I mean, we could try adding a bunch of even numbers together and show that it kind of always seems to work, but that's not good enough. I need a proof. I need some evidence, some ironclad demonstration that it's true for every even number all the time. How can I prove that the sum of two even numbers is even? I mean, it's obvious, but how do I show it mathematically? To do that, we have this proof by contradiction. What I'm going to do is I'm going to assume the opposite. My contradiction says assume the opposite. But I'm going to assume the opposite. So I'm going to assume that the sum of two even numbers is odd. I'm going to assume that. And I'm going to show that if that's true, something breaks. So how do I show that this is true? Well, what did we say about even numbers and odd numbers, right? I said that an even number was 2 times something, right? Even numbers are numbers that are divisible by 2. Even numbers are 2 times some n, where n, it's important to note here, n is an integer. Like a 1, a 2, a 3, even a negative. N is some integer. 2 times some integer number gives me an even number. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2, 4, 6, those are our evens. Even numbers are 2 times n, where some n number is an integer number. What do we say about odd numbers? That was 2 times n minus 1, right? And again, n is an integer. Some integer number. 2 times n minus 1. Why is this so bad at erasing? 2 times n minus 1. That's my odd number. So I'm going to say that the sum of two even numbers, I'm going to add up two random even numbers, and I'm going to show that that's odd. I'm going to do my proof by contradiction. So 2 times some number, call it n, plus 2 times some other number, call it m, two even numbers, is going to be an odd number. I'm going to call it 2 times some other random integer, call it k, minus 1. I'm going to assume that if I add two even numbers, I'm going to get an odd number. Right? Here's even, here's even, this is an even number, even, plus another even number, I'm going to say that it equals an odd number. So somewhere down this proof, I'm going to have something that breaks, something that is contradiction. What do I do? 2n plus 2m, well, what I can do, maybe factor out of 2. So I'm going to have 2 times some n plus m, okay, is 2k minus 1, right? That's what I've done. N plus n is just some number. And then I'm going to divide by 2. Divide by 2, divide everything here by 2, okay? So here I have some number n plus some integer m equals 2. 2 divided by 2 is k by itself, minus 1/2. And here we have a problem. What is the problem here? Well, n and m are both integer numbers. Integers. So a 1 plus a 2, or a 9 plus a 7, or whatever. Any integer numbers. So I'm saying if I add those two integer numbers, I'm going to get some, and here's an integer, here's an integer. I'm going to get something where it's another integer minus 1/2. And this is a problem, because this over here, some number minus 1/2 is not an integer, right? It's 1/2. So I'm going to get an integer. I'm going to say that some integer is equal to something that's not an integer, and that is not possible. Not possible. And therefore is a contradiction. Contradiction. Let me get a breath. Oh, you know what? There. Not possible. So therefore this is a contradiction. And that's my proof. Since that's a contradiction, what I can say is that my original theorem had to be true, right? My original theorem, therefore, 2 evens add to make an even number. Because I assumed the opposite, and I showed that it was broken, I got the situation that was not possible. 2 integers cannot add up together to make something that's not an integer. 1 plus 7 can't be 1/2, right? Not 1/2 breaks the situation and shows me that this is not possible. So if it's not possible that it's odd, that means it has to be even, my other idea. Okay? That's proof by contradiction. Do you want another example? And one more. One more example. Proof by contradiction is used a lot in math to prove all kinds of very interesting things. Very interesting things. So what if we said, oh, here's a good one. What if we said that I want to show that what do I say? If n is odd, if some number, if n is odd, then n squared is odd. That's my proof. I want to show that if you have an odd number, then n squared is also going to be odd. That's what I want to prove. So let's try a proof by contradiction. Assume the opposite. If n is odd, then n squared is even. I'm going to show that. I'm going to assume that's true. So let's find out. N is odd. Remember, what does it mean? What does it mean to be odd, right? That means that it is something like 2k minus 1. That's odd, right? What does it mean to be even? It means it's 2 times something, call it p. Even means it's 2 times something. So if n is odd, n squared is even. So if n is odd, I'm going to assume that n is 2k minus 1. So if I do 2k minus 1 squared, let's do our not killing puppies, 2k minus 1 times 2k minus 1. Foil this out together, distribute this. I'm going to get 4k squared minus 2k minus 2k plus 1. And this is going to be 4k squared minus 4k plus 1. That's what this is equal to, right? So this is n squared, right? This is n squared. And I want this to be even. I want this to be even. Is this here even? Is that even? Oh, question mark. Is that even? Or is it odd? How do I know? Well, what I can show you is that if I have an odd number times an odd number, right? I'm going to get this. This part right, let's do this green. This part here, this 4 times something is the same as 2 times something, right? 2 times this is 2k squared, right? But it's 2 times something. And this here is minus 2 times 2k, right? Oh God, oh God. Stop it, stop it, stop it. Let me show you that again. Let me show you that again. This part here is 2 times 2k squared, right? And I know that 2 times anything is even. I know that's true. And this is 2 times 2k, right? Just simplified it a little bit. And again, 2 times anything is even. So I have an even number, well, minus, whatever, even number minus an even number. And I know that that's got to be, whoa, that was not what I wanted to do. Undo that. Let's go like this a little bit. Let's go like this a little bit. Two even numbers minusing each other. I know that this is going to be even. I know that this is even. And if I do that, minus or plus 1, I have this plus 1, that's going to be odd. And that is a contradiction. That is my contradiction. Hold on, let me move this up. This is my contradiction. Contradiction. So I said that if n is odd, then n squared is even. But here's n squared. Here's n being odd. 2k minus 1, 2k minus 1, a bunch of squares. Multiply it out together. I got an even plus 1. That's going to be an odd number. So it's not even. It's odd, right? There's my contradiction. Therefore, 3 dots means, this means therefore. 3 dots. Therefore, if n squared, if n is odd, then n squared is odd. And that is my proof. Q B, D. So that's a proof by contradiction. Assume the opposite. If n is odd, then n squared is odd. I want to prove that. So let's say if n is odd, then let's pretend n squared is even. I show you how that cannot be true, right? I had an even number here. I had an even number, two even numbers. 4k squared is even, minus 2k, minus 4k here is even. Two evens minus each other makes an even number. I showed you last time. Plus this 1, right? This means it's an odd number, right? This means even plus 1 has to be odd, and therefore it's a contradiction. So my original idea had to be true. So this is the idea behind your proof project. Okay? You can do some research. You can look up the list of things. Let me show you the thing again. So on this document here, I show you lots of ideas of different proof projects. Down here is a bunch of things you could do induction from. Any of these are induction proofs. The sum of combinations, here's an interesting one. If you add up all the combinations, that's 2 to the n. The arithmetic sum formula, you could do this by induction, or the geometric sum formulas that we did at the beginning of the semester. Remember those arithmetic sum and geometric sums? You can prove any of these formulas down here. This is a fun one. This is maybe not an induction proof, but it uses something interesting. There's some videos about this one. If you add up an infinite number of numbers, 1, 2, 3, 4, 5, for all the numbers, it adds up to -1/12. Related to what we did earlier about adding up all the numbers, you get that formula. Very similar. This is a good one here. 1 plus 1/2 to the n. Add up all those to infinity, it equals 1. Interesting number. I think I did a little bit about that. And then here's some other ones. Prove that sums are 2 even numbers is always even. Things like that. We talked about even and odd numbers. A lot of proofs you can do with that. And then there gets to some interesting proofs, some more esoteric proofs. Prove that square root of 2 is irrational. That you can do by contradiction. You can, here's the sum of odd numbers one we did. Prove that 0.999 equals 1. That's a very interesting proof there. Every odd number is the difference of 2 squares. And then there's a lot of other things, the Monte Hall problem, Rubik's Cube solutions, pigeonhole. All of these things here are going to require some research. If you research those, Goldbach conjecture, yeah, a lot of really interesting things here that we can do. Archimedes approximation of pi. This is way back in Archimedes' time, BC 2000, whatever. So a lot of really interesting proofs out there. If you want to show any of these things, do some research about them, demonstrate the proof, explain the proof, and then we'll see if I have you make a video or if we can come in and do the proofs in person as a presentation. Okay? As always, contact me with any questions. Email me or contact me on Schoology. Leave me a message on the Remind. Either way, I'll be available all next week. I may be posting some other videos if people have questions. But here's the idea of induction, proof by contradiction, and a direct proof. One of these ideas I would like you to do for your video, okay? For your proof project. We'll talk about how to turn them in. You can turn them in again on Schoology, or if we're back, hopefully you can turn them in person. That would be good. Okay. Good luck out there. Let me know if you have questions, and until next time, see you later.